All right, good afternoon, everybody. Welcome to lecture 25. We're going to be getting started a little bit late today because we spent a bit on homework 5 discussion. And so this is going to be a bit of a shorter lecture, and then lecture 26 might be slightly on the longer side, but not too bad, hopefully. We're going to be starting a new unit today. So let me go ahead and share my screen, and we will return to this course map that we've seen so many times, which might have looked really strange and arcane at one point, but is starting to make more and more sense as we look at it. So at least hopefully, maybe that's overpromising. But so the path that the spacecraft is on is the kind of illustration of orbital mechanics. So we spent several lectures on that. We spent a good chunk of time on estimation theory, which is the mathematics that's the basis of everything else that we've worked on. We talked about triangulation and trilateration, so that's Earth to space and then space to Earth based navigation. So can we use spacecraft to navigate on the Earth? That's GPS. Can we use ground stations on Earth to navigate in space? Think Deep Space Network. We had a one-off lecture on inertial navigation, and that is using inertial measurement units or gyroscopes and accelerometers, essentially like the inner ear of the spacecraft to tell whether it's being pushed or to tell whether it's spinning. Right? We talked about that. Then we went and talked about star trackers for a while, and we spent 4 lectures on how star trackers work. And we spent then 3 lectures on Kalman filters. So down on the bottom right, that's not a robot head, that's my best depiction of the Apollo guidance computer. And so that is kind of a visualization of, okay, well, this is the algorithm that the flight computer needs to be running all the time so that it can consistently and continuously estimate what is, so that's sequential estimation. It's going to be estimating its state over time. And homework 5 is going to be on Kalman filtering. Our very last unit is this green image, which is optical navigation. And that's going to be what we spend the rest of the semester on. And we've actually only got 3 more lectures. We've got today, where we're going to start talking about something called horizon-based OpNav. We've got next week, we're going to finish the discussion on horizon-based OpNav. We've got a few guest lectures from colleagues of mine that won't factor into your homework assignments. Those are just going to be completely for fun. And then I've got an also just for fun homework or lecture which describes how to do the optional homework 7, which is also optical navigation. It's just a different type of optical navigation. That's called terrain relative navigation, which is a little bit different. And so that's pretty much it. So we're within a stone's throw at the end of the semester. Hopefully each of these things make a little bit more sense than it did at the beginning of the semester. So we're going to be starting with optical navigation, which I abbreviate as OpNav. Right, so OpNav is going to be the topic of the next 2 lectures. And so I want to start with a quick kind of visualization here. So I'll take a couple of volunteers from the audience, right? And I'll just say this. You can navigate using these images. So I'm going to draw 3 images. First, I'm going to attempt to draw 3 rectangles, so wish me luck. And then I'm going to draw 3 different images. And each of these has enough information for you to navigate. What do I mean by navigate? To estimate your state, or at least your position, maybe not your velocity. One thing at a time, though. There we go. So let's start on the left. Optical navigation implies cameras, and it also implies taking an image of something other than stars. So I guess technically you could argue that star trackers are a form of OpNav because they involve cameras. Maybe, sure. We're going to be talking about taking pictures of planets and moons and things that are made of rock and gas as opposed to the stars, right? Things that reflect light rather than emit their own. So I'm going to draw an unresolved image where you've got a dot and then another dot, and you know that this dot is the Earth, and you know that this dot is the moon. This single image gives you enough information to estimate your state. How? I'll take a volunteer from the audience. What would you do in the unresolved OpNav regime?
You also need time, correct?
Ah, okay, I like it. I like it. So what would we do with this information?
if you know the time,
Mm-hmm.
then you can use ephemeris or the positions of the planets, and then so you know where they are in real space, and then it's very similar to a star tracker if you know the angle between them, and then
So I'm going to poke on one thing you said, because I think you're right, but very similar to a star tracker makes me think that you're trying to estimate your attitude. But in this problem, you know your attitude. You're trying to find your position. How would you determine your position if all you had was a line of sight direction to the Earth and a line of sight direction to the moon?
you also know their size in the image.
In this image, they are unresolved, so they look just like stars, but you know because of reasons that it's the Earth and the moon instead of stars. Well, this one's tricky, isn't it? Does this sound like something else we talked about at one point? It's like you've got a line of sight direction to a known position and then another line of sight direction to a known position. And
Similar to Gibbs method,
it is. So
right?
you could, if you had measurements over time, this would be Gibbs method. If you just had this one image, this would actually be triangulation. I don't know why I tabbed to this, but this would be a form of triangulation because you would have, there we go. If you knew where the Earth was and you knew where the moon was, and you had your line of sight directions to both of those, and let's assume for a minute that you've also got a star tracker running on the side so that you know your attitude, right? Then it's just a position estimation problem. You could use the techniques that we discussed all the way back in lecture 16 to triangulate in this unresolved OpNav regime. Does that track? Does that seem reasonable to you?
Do you not? One second.
All right.
I Yeah, that's seems reasonable.
That seems okay. I don't love the level of confidence with which you said that seems reasonable, but that's we can talk about it. Don't worry.
Yeah,
Um,
I have a question.
yeah, I got an answer.
Since you only have line of sight measurements, could you use Gauss's method?
So, you know what? You're absolutely right. I got it backwards. This is Gauss's method, not Gibbs' method. So let's assume that you had several measurements over time. Then it basically becomes an orbit determination problem. You can get your full state that way. But just from this one image alone, not any other information, except maybe you know your attitude because you have a star tracker, right? Something like that. Then you can estimate your position just with this image. You can find the centroid of the moon, get its line of sight direction in the local frame, convert that over into the inertial frame, do the same thing with the Earth. Two intersecting line of sight directions has one solution. Now, you would still need to know where the moon is in some global sense and where the Earth is in some global sense. So you would need something like ephemeris data or spice kernels or something like that. But this is ultimately a triangulation problem. But so that is, while that's neat, we're going to compartmentalize. We're going to move on to, this is an unresolved image, which is to say that the points of light are just that, they're points of light. So then what I want to say is we have the body has been resolved. And so that would be an image that looks a little bit like this. Let's say this is the moon. And let's further say that it's partially shadowed. You can navigate only using the information in this image. How do we do that? I'll take a different volunteer, whoever else is feeling brave.
I'll try.
Sure, what do you think?
So based on like the part that's shadowed, then maybe you could tell what position the sun is in, and
Ooh, I like
maybe you
that.
get like a line of sight direction of the moon and the sun.
I like it, although it would be a little bit tricky to estimate where the sun is from the information in the image.
Oh yeah.
But that's not a bad idea. Now, I want to move away from triangulation because this is actually not a triangulation problem. This is going
Oh.
to be something else where we're only using the moon in this image. I guess maybe I should label it that this is the moon. Do you want to take another try or do you want to pass off to somebody else?
I guess I'll try again. Um, hmm.
And I should be
So,
clear, this is not something I've taught you before. So this
oh,
is new content. This is not some remix of the other things.
oh,
Just
okay.
using your imagination. It's like, what would you do if you had an image like that?
Hmm. So this is just like, it's just one image, like just a snapshot.
Yep, just a single snapshot of the moon.
Hmm. Maybe you could use like the shadow to determine like what phase the moon is in and then relate that to like time on Earth or something.
Okay, that's not bad. So, but remember, you're looking for your position, right? So
Yeah.
then if you want your position relative to the moon, well, there's really two things that you need to get your position, right? That's range and bearing, right? So your bearing comes from the apparent direction to the moon. How would we find the range? Like from only this image, how would you know how far away the moon is from you using no other information?
Hmm. Oh, maybe like how much of the shadow you can see. It
Hmm,
like could tell you how far away you are, maybe.
you're getting pretty close. I would move away from the shadow because this would work just as well if it was a full moon and just as well if it was a thin crescent of a moon. You could
Oh,
still use this method. Yeah. So here's the idea, because I think you've certainly been very close for a while, so I don't mind giving you a bit of a hint. If you know where the sun is, you can start navigating by, okay, let's draw lines from the left side of the image until we hit something bright. And we're going to call these horizon points. There's another one. There's another one. And then these horizon points should fit to an ellipse. So if you fit an ellipse to the horizon points, now you've found the moon in the image. And what I would contend, and this is an oversimplification, and you'll see in this lecture that this is an oversimplification, that the radius of the moon in the image gives you information about its distance, right? Because
oh, yeah.
yeah, the wider it is in the image, the closer you must be to it. And then the narrower, the smaller it is, then the further away you have to be. And then the centroid of this ellipse would give you information about bearing, the line of sight direction from you to the moon. And if you have range and bearing, you've got your position. And so this method has a name, and it is called horizon, because you're using the lit horizon based optical navigation. Now there's a third regime, and thank you, Italia. I'll take a third volunteer for the last one though. And this is where the surface has been resolved. And I guess if we're being clear, I should probably, we'll call this like interplanetary triangulation. So I'll take a third volunteer, and you can kind of imagine where this is going. Let's say you take an image of the moon, and it looks like this. You're really close, and this is space. And then you got a big old crater right here. And you've got a smaller crater here, and another crater here, and another crater here, another crater there. There we go. And that's the moon. So the entire surface is resolved. You can clearly see surface features of the moon. Right? How would you navigate in this regime? And I know that some of you, this would be too easy of a question to answer, so there shouldn't be any radio silence here. Any takers on surface-based navigation? Oh, y'all are killing me. I'm gonna have to start calling people out. I have it on good authority that some of you are doing research on this for your master's degree. So I think you know who you are. How do you navigate with a picture of the moon like this?
You can identify crater rims
There you
and
go.
attempt
Thank you,
to
Max.
figure out which ones you're looking at. Yeah.
I appreciate you. I know you're shy today. Sorry to put you on the spot like that, but you're killing me. No, you're absolutely right. If you can identify surface features in a global sense. So you could say, okay, well, look, I recognize this crater and this crater and this crater. And you get the centroids of those craters. You go, well, look, there's the center of one crater, there's the center of another crater, there's the center of another crater. Then what you have, let's say, I don't know, there's 3 of them. Really, there might be more, but for now, let's say you found 3 craters. If you have the line of sight direction in your local camera frame to 3 known points which exist in some global frame, then that's called the perspective endpoint problem. The perspective endpoint. Perspective endpoint is the cooler older brother of the triangulation problem, where you're not assuming that you know your attitude to start with, right? So you actually don't know your position or your attitude. You're trying to get both of them at the same time. It's kind of the triangulation plus star tracker all together is called the perspective endpoint problem, which thankfully is a very well-studied problem. Now, to be clear, this is homework 6. We will be doing this on homework 6. And then this is homework 7, which is optional. But I just thought I'd mention that for anybody that wants to bark up that tree of homework 7. So this method, oh, sorry.
Sorry, quick question.
Yeah.
So there's some catalog of lunar craters similar to the Hipparcos catalog, or analogous to the Hipparcos catalog for stars.
Yep, there sure is. Absolutely. And I should be clear that there are several methods of terrain relative navigation. This is just one of the methods that I think is worth discussing, but there's absolutely others. This is like, I guess we'll call this crater-based TRN. Sorry, did I fully answer your question, or I didn't mean to cut you off?
You did answer it.
You good? Okay, cool. So I thought I'd mention all 3 of these because all 3 of these are OpNav. They're using optical measurements like camera, images, light-based images, to determine your position in space. We will be focusing on horizon-based OpNav for this next unit, for the next couple of lectures. And so this will be a unit on horizon-based optical navigation. But then for our final lecture, we're going to go back and talk about solving this problem, right, of using craters. So we'll start with horizon-based optical nav. There we go. And now, if those of you, I know you're swamped with homework 5, but if you take a peek at homework 6, I've posted an image from the New Horizons mission of Pluto. And using only the information in the image, you can estimate your position relative to Pluto, which I think is pretty neat. And so that's going to be homework 6. And what we're about to do is go through, after a brief introduction, a very long derivation. It's going to be two solid lectures of derivation for one result, which is the equation that gets you your position relative to the moon or the Earth or Pluto or whatever you like in the image. So it's going to be a little spicy. So this is going to be you can think of this as the final boss, right? We're done after this. Once we go through 2 kind of somewhat long-winded lectures where we go through this derivation, we'll get to the point where we can solve the horizon-based OpNav problem, and you can get OpNav running on your computer for homework 6. And then homework 7 is going to be a one-off lecture for anybody who's interested in TRN. And then we're done. So to be clear, optical navigation is the use of images for navigation. Optical navigation, or we're just going to say OpNav, refers to, actually, you know what? I'm going to skip the second bullet point. Apologies, you can erase that. I just realized that my second bullet point is redundant. So when we are very far away from a celestial body, and I use the phrase celestial body because this works equally well on planets and moons. it appears as a point source of light. I'm just going to say point source. And in this case, the best we can do is find its centroid and estimate some inertial bearing, the line of sight direction from you to the planet or moon in the inertial frame or in the global frame. And if you have multiple of those and you know where the thing is, you can triangulate your position, but we're going to leave that out for now. As we move closer, the celestial body, I was going to say the body becomes fully resolved in the image. That is to say, it's not a pixelated mess. You can actually make out details. And so in this case, processing images to find a body's horizon line and estimate relative position is referred to as horizon-based optical navigation. Or OpNav. So this is where I'm going to be a bit hypocritical. Strictly speaking, OpNav is any use of an image to navigate in space or on Earth, right? When I say OpNav, I mean this. I mean, we're taking an image of the Earth or the moon, we're finding the lit limb, we're fitting an ellipse to it. This is what I mean when I say OpNav. If I'm talking about crater-based nav, I'm going to call it crater-based nav, or I'm going to call it terrain relative navigation. And the problem on the left, we don't really discuss all that much in this class, but it's something that you could certainly look into if you wanted to. But OpNav is the middle image when I use the words OpNav. All right. So questions so far? Or do we feel all right up to this point? As we are about to embark on a mathematical adventure, the likes of which you've never seen. And we're going to go through what in my notes is 8 straight pages of math to talk about how you would solve this problem. And you might be thinking, there's no way it's that hard. Au contraire, this is pretty spicy, but this is a solvable problem. You might be thinking, well, look, Paul, can't we just take the apparent center of illumination of the body, and then there's your bearing, and then just fit a circle to the thing, take the radius of the circle, and then there's your range using similar triangles? Yes, you can, and that will work, and it will get you a low accuracy position estimate. I mean, it will work. I mean, you'll be wrong, right? And the question is, well, how right do you want to be? And it's been demonstrated. This method of navigation flew on Artemis 1. It was demonstrated that using nothing else except horizon-based OpNav, the spacecraft could navigate from the moon to the Earth with enough precision that it could hit the reentry corridor and the crew would have survived if this was the only game in town. If we lost DSN, if we lost the star trackers, if we lost everything, this would still get the job done, which is pretty that's pretty cool. I like that. But that means that we can't leave any juice in the lemon. We got to keep squeezing to get the most performance out of this image possible, right? And I should be clear, it wouldn't be a single image. You'd be taking multiple images over time and processing each of those, right? But this is like, in theory, in much the same way that a human would not die from malnutrition if they ate only potatoes, or so I've been told. I think you might need some vitamins, but like in theory, that has all the macronutrients you need. Then a spacecraft can navigate with only this, and which I think is pretty spiffy. Of course, I'm biased, right? I'm on the team that works on this, so obviously I'm going to say nice things about it. But yeah, so let's get into the first topic, which is the global shape of a celestial body. That's our first topic of discussion. So let me start with a question. And this is a rhetorical question, unless you feel like keying in your microphone to answer. Is the Earth a sphere? And the answer is no. It is an oblate spheroid. You might be familiar with that term. Oblate spheroid is one where the cross section of the equator is roughly a circle, but the cross section of, if you were to take the Earth and slice it along the prime meridian, it's wider at the sides than it is in the middle, which I'm trying to kind of draw like, imagine that a perfect circle would be something more like that, right? That's the Earth. I guess that's not exactly the best diagram ever, but you get the idea. You've learned this in school before. It's an oblate spheroid. Is the moon a sphere? And unless I mention otherwise, I mean Earth's moon. Is the moon a sphere? The answer is, yeah, kind of. It's close enough to a sphere that if you wanted to approximate it as a sphere for the purpose of, say, your homework assignment, it'd be good enough. Similarly, Pluto is close enough to a sphere that we can treat it as a sphere for your homework assignment. That's also good enough, right? So some things you can approximate them as spheres, some things that you can't. What we really need is a shape that is more general than spheres, and we can say that spheres are a special case of that shape. The same way that rectangles cover things more general than squares, and squares are a special case of rectangles, right? So the general shape is called a triaxial ellipsoid. So a planet, say planets, dwarf planets, such as Pluto. Don't get me started on whether or not Pluto's really a planet. That's a long argument. And moons are often well modeled as triaxial ellipsoids. Triaxial meaning having three axes, right? So a triaxial ellipsoid works like this. X squared over A plus Y squared over B. I'm sorry, these are squared. X squared over A squared plus Y squared over B squared plus Z squared over C squared is equal to 1. And that describes what is basically a football shape. You can imagine here's your football, and then it's got some, there we go. There you go. There's your triaxial ellipsoid, where if here's the true center, then this distance to the bottom, we'll call that distance C. This distance over to the side, we'll call that distance B. And then this long distance here, we'll call that distance A. Right? There's your triaxial ellipsoid. And I should be clear that this equation is true in the principal axis frame. Not necessarily true for general things. So this is in the principal axis frame, the equation becomes this symbol. So some common triaxial ellipsoids you might have heard of this one. If A and B and C are all the same number, that's a sphere. I feel like we've bumped into those before. That's a more common shape. If A and B are the same number and they're both bigger than C, which is to say it's got two axes that are of some regular length and it's got one shorter axis, that is an oblate spheroid. This is the Earth. Well, of course, the Earth is really an infinitely complicated shape, but it's better modeled as an oblate spheroid than it is as a sphere, right? The general case would just be A is greater than B is greater than C. This is the general case of a triaxial ellipsoid. So now here's some neat tricks that we can play with triaxial ellipsoids. So I'm going to say let the point P lie somewhere on the ellipsoid's surface. Okay. If that's the case, then the vector p in the p frame, okay, that's a lot of p's. So this is x, y, z, still in the p frame, where p in this case is the principal axis frame. Or you can think of it as the planet frame, right? If p is this and a is this, a is 1 over little a squared, 1 over little b squared, 1 over little c squared. You could think of this as the shape matrix, as the matrix which contains the information about the planet or moon. So we're going to call this the planet shape matrix. If this is P and this is A, then this is true. P transpose A P is equal to 1, which is pretty neat. So we've got a matrix which describes the shape of the planet, and every point on the surface of the planet satisfies this equation, which is pretty cool. And that's absolutely going to be useful for us moving forward, because points, and I'm not trying to spoil it for you, but points on the surface of the planet are these red points that I described in the beginning of the lecture. That's kind of what we're ultimately going to be building towards. So just kind of, that's why we're barking up this tree. Now, since AP is diagonal, we can easily invert it. So AP inverse is just A squared, B squared, C squared. All right. Now, what if we wanted to express the planet's shape in a different frame? Well, let's consider this. If PP is really PC, where C is the camera frame, the relationship between them is just going to be T from C to P, right? The attitude transformation matrix from the camera frame to the principal frame or the planet frame. If we substitute, then we would say this, okay, P transpose AP PP. That's the same thing as PC transpose T from P to C, because we're transposing this guy. AP T from C to P, EC. So all I did was substitute into this equation. Okay, now I'm going to define all of this as AC. So now what we've essentially done is, by front multiplying and back multiplying the planet shape matrix by the attitude transformation matrix from the principal frame to the camera frame, we arrive at the planet shape matrix in the camera frame. We're going to call that AC. Okay. So now if we keep moving, what we're really saying is PC transpose AC PC. Well, that's still equal to 1, right? All we did was make some substitutions and rename some things. So what's pretty cool about that is that this equation, which describes the relationship between the planet shape matrix and points on the surface of the planet, is true in the principal axis frame, but is also true in the camera frame, which is going to be, pardon me, it's going to be very useful. So I'll say thus, we can rotate the shape matrix, the planet shape matrix, into another frame by this. And you can think of it as C's on the outside, P's on the inside. That's kind of the way I think about it. Okay, so that's a good natural pausing point. So why don't we stop and ask if anybody has any questions so far, or has this been hopefully pretty straightforward? We're still just laying the foundation for the work we're going to be doing later. And I'll say this, if anybody here has solved a Rubik's Cube before, I know there's different algorithms that you can use to solve a Rubik's Cube, but the one that I know, it actually starts to look pretty orderly at the beginning, and then it starts to look worse and worse and worse, and then all of a sudden it's solved. And I think that's how this derivation is going to go. So hopefully so far it seems pretty orderly. Hopefully it's going to stay orderly for at least a little while. And then before the end, you're going to be like, dude, what the heck are we doing? We are so many levels of abstraction deep. And then all of a sudden I'm going to say, we're done, and show that, you know, we've actually reached the end of the derivation. So that'll be mostly next class, but I want to see if we can't get through, maybe one more page of stuff. Let's see if we can keep pushing for now. Okay, so the next kind of topic is the rotation and translation problem setup. Okay. So suppose we want to consider a rotation and a translation with respect to the principal frame or the planet frame. So this is the more general case of OpNav. OpNav can be used to solve for position and attitude simultaneously, but you know, we're not going to get into all the gory details, but the attitude is not super well observable, what we'll find, and that in practice, it's often better just to use star trackers or to use other techniques for attitude. So we're going to start off by setting up the general problem, but then when we actually go through to solve it, we're only going to be chasing down position. Okay. Now, suppose that we have planet, and it's got some equator. It's got some prime meridian. Okay. And let's say that its center is right here, and that it's got a point on the surface right here. Okay. And we're going to call this vector P. And let's say that you've got a camera floating out in space, and it is measuring a line of sight direction to the center of the body and a line of sight direction to the surface of the body. This is where we're going to be really careful. In the OpNav derivation, R is this way, from the camera to the center. Right? Then we're going to use zeta, which this is how I draw zeta. You might have seen other professors draw zeta like this. I draw it like this, or kind of like that's. I've never drawn zeta the same way twice in my entire life, but we're going to be using the letter zeta, so bear with me, at least for the next chunk of the derivation. So I'm going to say that zeta is the vector from the observer to a point on the surface of the body, and r is the vector from the observer to the center of the body, which is ultimately your position, right? It's just backwards. Right? By this definition, zeta is r plus p, or you could think of p as being zeta minus r. And you could say that P in the principal frame is T C to P zeta in the camera frame minus R in the principal frame, which is the same thing as saying it's zeta in the principal frame minus R in the principal frame. Okay, so now this idea here, which hopefully makes sense, we can actually simplify this. We could say, okay, P with a hat on it is equal to this matrix times zeta C with a hat on it. And you're going to smack me because now I'm using a hat to mean a third thing. It's not a unit vector like it was in the star ID and star tracker lectures, and it's not the current best estimate like it was in the Kalman filter lectures. It is a homogeneous vector or homogeneous coordinates. So P hat is P as a vector and then the number 1 tacked on at the bottom. And similarly, zeta C hat is zeta C as a vector and then a 1 at the bottom. So these are both going to be 4x1s. Right. Later, I'll think of some better way to describe this, but this is where we are for now. Please don't be too mad. So then this is this here, RP, with the vector, not the hat, because this is just a 3x1 vector, and then 0, 0, 0, 1. So this equation here is the same idea as this equation here, expressed in homogeneous coordinates. So I'll put that clearly. We can use homogeneous coordinates to express rotation and translation simultaneously. You might have seen this if you've taken robotics, or you might have seen this in the context of like a dynamics course, that this 4x4 matrix really contains a rotation and a translation at the same time. Okay, so then we're going to need this because we're building towards something a little bit more complicated. So the next topic I want to get into is something called the quadric locus and the quadric envelope. So we're going to go through this topic and then we're going to wrap up for the day. And we won't be quite halfway done with this lecture, but that's okay because we have a little bit less time than usual. So remember that P transpose AP PP is equal to 1. That's from before. Okay. Well, then you could just as easily say PP transpose AP PP minus 1 is equal to 0. Okay. Now we could express this same idea in homogeneous coordinates as P with a hat. So this is going to be a 3x1 vector with a 1 tacked on at the end. Transpose, and then some matrix that looks like this. A P 0, 0, 0, 0, 0, 0, 1. So it's going to be a 4x4 matrix. Okay. Multiplied by PP again is 0. So this is a 1x4, this is a 4x4, this is a 4x1. So when you're done multiplying, it had better be a 1x1 or a scalar, which is just 0. And this matrix, A, P, and then zeros on the right and the bottom, and then a 1 on the bottom right, we're going to define this as being QP. Okay. If QP is full rank, or rank 4, it describes a proper quadric locus. Okay, what the heck is that? A proper quadric locus is the set of all points lying on a non-degenerate quadric surface. And in this case, non-degenerate does not mean that it is not a weirdo. It means a quadric surface is generally an ellipse or an ellipsoid like this. But if you lost rank, then you could maybe end up with like a pancake shape. So a 2D ellipse in 3D space would be a degenerate quadric surface, right? You've kind of lost some information. It's not the way it's supposed to be. That's the idea. So think of a sphere or an ellipsoid. Okay. So we're building in the direction of having these mathematical tools that can help us solve this math problem. So let's keep pushing for a minute. We can substitute because we as navigators do not have access to points on the surface of the moon. We have access to this zeta, which is the vector from a spacecraft to a point on the surface of the moon. Really, we don't even have that. We have zeta normalized, which is the line of sight direction to a horizon point. But for now, let's turn our attention to zeta for a minute. So if we take this equation, we say, okay, zeta c hat transpose times this. So what we're doing now is we're substituting in that PP with a hat is this 4x4 homogeneous matrix times zeta c. So if you transpose this, we're going to plug into what we had before. So this is now T from P to C. This is negative RP transpose 0, 0, 0, 1. So we flip that matrix on its side. And then we pop in the QC matrix, which is A, P, and then zeros and a 1. And then we substitute again, and this is going to be T from C to P. RP should be a minus 0, 0, 0, 1. And zeta c. So we just took this same equation as we saw a second ago, PP transpose QP, PP is equal to 0, and we just plugged in the fact that we can substitute a point on the surface for a rotation and a translation multiplied by a, oh, was not trying to erase that. Actually, I didn't even know I could erase it that way. Okay, I found a new button on my pen stylus. Multiplied by a vector from the spacecraft to a point on the surface. And we can actually clean this up. This whole interior, if you're willing to do some math, which I'm not going to make you do right now, simplifies to this. So we're going to get zeta transpose times some big matrix, which looks like T, P to C, AP, T, C to P, negative T, P to C, AP, RP, negative RP transpose, AP, T, CP, and RP transpose, AP, RP minus 1. That's what we get if you simplify. If you don't believe me, then that is an exercise left to the reader. If you do believe me, then congratulations, we can keep moving. Although if I did make a mistake, I'd like to hear about it. Now, we can simplify this even further if we say, okay, well, remember, AC is T, P to C, AP, TC to P. That's not new. We had that before. And then if we say, okay, well, isn't negative T, P to C, AP, RP, is that the same thing as just negative ACRC? Like we've just put it in the camera frame, right? And then similarly, so I guess this is really 3 different bits of information here. RP transpose AP RP minus 1. Well, we already know that this is the same thing as RC transpose AC RC minus 1, right? So this one on the right and this one on the left are not news. Those are already equations from earlier in the lecture. This one in the middle is news, but it hopefully makes some sense. And so we can simplify even further and say, thus, we have zeta C transpose times this matrix, which is AC negative AC RC, negative RC transpose AC, and RC transpose AC RC minus 1 times zeta C, again, is equal to 0. And this whole thing here is QC, okay, where QC is a 4x4 symmetric matrix. Hopefully it's clear that it's symmetric from the way it's defined, describing the proper quadric locus in the camera frame. And so we've reached the first of what I call the understanding checkpoints, because this lecture is going to be a bit circuitous. And actually, we're going to stop right here, basically. So this understanding checkpoint, hopefully this makes sense, right? So we'll just pause for a minute, right? We've got a great big matrix, which is kind of ugly. But what is it built out of? Well, it's built out of the planet's shape matrix in the camera frame and the relative position of the planet and the spacecraft in the camera frame, which, by the way, is what we're after. Like this is the secret stuff. Like we're after RC. And it involves these line of sight directions, which are not strictly line of sight, because these involve distance. So we're not quite where we want to be yet, right? But you've got points on the surface of the moon as seen by the observer. You've got the position of the observer with respect to the moon, and you've got information about the shape of the moon. And you could just take the word moon and substitute out Earth or, you know, Pluto, whatever else. All of these exist in one equation, which is kind of neat. So we're not quite to the end of actually, we're not even halfway done, but I feel like that is a good natural stopping point. So I'm going to make a note to pick up here next time. And I think that is good enough for one day. So next time we're going to do about 2/3 of the derivation, and we'll ultimately get to solving for RC. But anyway, thank you very much, everybody. I hope you have a great rest of your day. As a reminder, before everybody leaves, there's no lecture on Monday, right? Monday is April 8th. It's going to be the total solar eclipse. It's going to be the last total solar eclipse that is visible in the United States for 20 years or so, I've been told. And I will not be here to teach. And I hope that y'all either take the time to go see the eclipse or take it for your mental health or to work on a different class or something like that. But no class on Monday. I will see you a week from today. Take care, everybody.